So what is today's plan? I just want to share with you all that the timeline for this bootcamp is for day 1, right? Day 1.1 actually is 10 o'clock to 12 o'clock. And then we have 1 hour break as long as day 1.2, and it goes for the same for the day 2 and day 3, which is 12 March and 13 March. So theory and practical. First half is theory, second half is practical, okay? Then nature of lessons is that the theory of lessons will only cover the basics of AI and it's more like theory focused. Okay, whereas the practical lessons will cover more of coding of AI deployment. So to get what your IT students are very good with, which is programming. So that'll be 1.2. To learn 1.2 first, you need to learn like the theory of how it works behind the scenes. So that's 1.1. When in doubt, you could simply ask the MS Team chat. So there'll be assistants to help you with your doubts. So now, without further ado, we'll start our day 1.1 basics of AI. So we have gone through ice-breaking games. I hope you have been warmed up by the quizzes. Okay, so we now go to introduction of deep learning and neural networks. Karthik, please.
Okay, so thanks, Samuel. So for today's session, now we're starting the theory. So today's session is mainly about deep learning and neural networks. So the important question that we had to first of all ask ourselves is, what is AI? So okay, the thing is, by now, after being in at least 1 year in this school, it's impossible that you guys don't know what AI is. So, but regardless, I'll just go through it. AI is pretty much artificial intelligence, and it has been a subject of intense media hype. Pretty much the reason why we are all even aware of it, in my opinion. And it has grown so much to the point that it has been involved in various things like chatbots that we come across, even virtual assistants, or even self-driving cars nowadays. So with that being the case, by the end of the bootcamp, we hope that you'll be able to do 3 main things. Firstly, differentiate the different world-changing AI developments available. Then go on to develop some AI agents, which we'll be slightly going through as part of the bootcamp. And finally, utilize these different AI agents to solve possible real-world problems. But I think for that, it will take you, I think we need you to probably further study on what we have taught in the bootcamp. So moving on, now we'll be So now I'll be basically covering the 3 different AI developments that we are talking about. So basically AI is quite a broad topic. In our modern day, it can refer to anything as AI. So quite a lot of things is AI. So it is important that we know what are the different subcategories in AI. So AI itself is actually a simulation of human intelligence in machines. That's basically like the broad explanation to what AI is. And basically, AI is like a development of algorithms to enable computers to perform tasks that usually require human intelligence or human interaction. So you want to minimize that as much as possible, which is why the whole concept of AI was brought in. Then moving on, we have machine learning. So machine learning, like what you can see in the image below, is actually a subset of uh, artificial intelligence. And it particularly focuses on developing algorithms also, but by learning data that is provided to it. And basically what it does is to learn from this data and learn from this experience basically, and improve its performance over time to perform that certain task. And then finally, deep learning. As you can see yet again, it's a further subset of machine learning. So the whole point of what is deep in deep learning. So basically, deep in deep learning suggests the point of utilizing artificial neural networks with multiple layers, which is why the whole concept of layer is the reason why it's called deep learning. And having these layers of neural networks actually helps to allow the machine learning model to learn intricate patterns from the large and vast amount of data that's provided to it. And the good news is that it's gained significant attention and success in recent years. And some of the things that we have come across, like in our daily lives itself, are like image recognition, speech recognition, and natural language processing. And you guys might have heard of these terminologies before. And let's be real, the whole reason we are covering this topic is because this is what we expect to be a significant portion in our lives in the next few years, especially as ICT students. So yeah, moving on. Okay, now let's get into more intricate topics in the form of a neural network. Pretty much, this is to give you a teaser of the areas that we're going to be covering throughout the rest of the workshop. So, what is a neural network? So, first of all, before understanding what a neural network is, one thing to note is this whole concept is something that was inspired from our human brain. So if you shift your attention to the image shown on the screen, so what you see on the left of the image is actually the neurons in our human brain. And these things, you can see, if you can see how it's similar to what you see on the right of the screen, which is the neural networks created. So what happens is in these neural networks, they have nodes in them, and these nodes are interconnected to each other, and this is how they form the different layers. And the complexity of a certain neural network is actually determined based on the number of nodes and layers it has, and this will determine its learning capacity. So the more the nodes and layers you have, the higher the learning capacity. So that's like the most broadest explanation of what a neural network is. So now we'll be going deep. Since now you have like a basic idea of what it is, now we'll be going deep into what it actually is. So next slide. So let's actually go on to understand what a neural network is. So now that I give you an idea that it's something related to like neurons, receiving information, processing information, all. So the whole idea of what neurons do is like what we do also. Our brain receives some form of input, then we process that, then we give some form of output, like we give a response to it or something after understanding what someone has told us or something. So something like that. So similarly, what happens is some form of data will be provided to the neural network to the input layer, and the hidden layer will go on to process the data. That's where your mathematical calculations and all come about. Then after that it has processed the data, it will go on to see the processed data and provide the final decision or prediction, which comes in the form of the output layer. So let's go deep down into it. Next one. So, okay. Now I gave you a tiny teaser of what are input layers. So okay, now let's actually look at what are the different things like you can how is so-called applied in real life. So for instance, to put it simply, the things that we provide in the form of input are like specific features of our data, or to put it simply for you guys to understand, certain columns of data are what's that given to the input layer. So let's maybe take like example. Okay, so if you're a DS student or anyone who takes like a ML module or something, you will come across a very like common example. Our school always likes to bring up this Titanic data set example, and so I think it's best we use it also. So usually how they use it is they want to see in this Titanic example, everyone, quite a lot of people died in it. So basically, they want to predict based on the data information of a person to see whether a particular passenger survived or not. So in this data set, there were information like things like age, the passenger class, basically like, you have your economy and all for your flight, something like that, gender, and so on. So each of these different columns of data will be provided to the neural network, which is in the form of the input layer. So you can see, and if you shift your focus below to the image below, so you can see that, like another example, if you to maybe predict the possible energy consumption, you can give like the number of people, season, above the day to the model, then you predict the possible energy consumption. So something like that, like a very basic idea. So going on to the hidden layer. So hidden layer is actually where the more complicated things actually happen. So now what we are showing on your screen is like probably a very simple example. So all of you must have come across go MX plus C. If not, there's no chance you pass your math in O level. So it's a linear equation, but instead of it being C, in this case it's B, because B, in this sense, we want to make sure we dedicate it to the bias that is possibly the machine learning model might experience. Bias might be a slightly a new terminology for you to maybe understand. So we will slowly go through it in the next few days. But if you're currently curious to know, you can go search it up or type on Google what bias is and so on to find out what it is. Then after that, basically what this correct. Basically what this equation helps us is to understand how the inputs, which are x, are combined and transformed, basically like what we showed in the previous slide, to produce a particular output, which is y. And y in this Titanic example is basically whether they survive or not. Yeah, so maybe 0 or 1, yeah, in the form of binary. So finally, output layer. Moving on to the output layer. Okay, sorry. Firstly, there's a bit more for hidden layer. So hidden layer, there's one more thing to actually cover. The thing is, you see, in y equal mx plus c, the m is actually referring to the thickness of our synapses of a brain, human brain. So synapse is quite a big terminology. So maybe you want to take a look at the image on your right first. So you can see on the top of the image, that's what the biological synapse is in our human brain. So that's how it is. So some of the people who created this whole neural networks concept tried to simulate how it would look like. So you can shift your focus to the bottom of the image, so you can see that's what the artificial synapses looks like. So that's what it refers to the M. So how thick it is refers to the M. And we also call it weights, and usually it's denoted by the letter W. So if you saw the equation just now, it was actually W, and it determines how much of a particular input is used. And after that, after it's passed, we have Y, and it's passed to the activation function. So moving on. So okay, you see, right? Let's be honest. Like what I said, linear equations, there is a limitation to linear equation. It can't. After some point, some of the outputs are actually force fitted into this linear equation. So it won't really give you the most accurate output, which is why we need activation function. So I'll be covering two types. Firstly, sigmoid. So what you can see here, especially on the right of the screen, there's this graph. So basically, the sigmoid function, what it does is it squashes the output y that has been calculated to be between 0 and 1. So it determines whether the neuron or the node has been fired, which is 1, or not fired, which is 0. So basically, fire and not fire is whether it's positive or not positive, something like that. So I hope you understand it in that point. But okay, the thing is, why I'm going to cover another activation function is, from what we realized is sigmoid didn't really perform well in the 1990s due to some limitations. But if you're interested, you can go on to search it out online and what they are. So what happened is, some more mathematicians decided that it's important we propose other types of methods to determine if the nodes are firing or not, which is why in our next slide, we will be talking about ReLU, which is, if throughout the next few years, especially for DS students, if you start doing machine learning, I think this is quite an important topic that you'll come across. So ReLU is actually a short form. The real name of the terminology is rectified linear unit, and it was proposed to solve the limitations of sigmoid. So you can shift your image to your attention to the screen, to the image. So this is what the current graph looks like. So what happens is, if you look closely to the x-axis, so if it's positive, then it just directly outputs that. If not, if it's actually negative, it just outputs 0. So that's how this is how basically it works. So if you want to learn more, you can read up once again. So basically, the equation is simply max x0, where X is the input, and this variable is like interchangeable to Y in statistics apparently. And like what I said, if the value is output positive, which means neuron is fired, else if negative, output 0 if neural network is not fired. So for those who have some sort of advanced machine learning knowledge, this is like something similar to your classification modeling. So yeah, moving on. We finally have our output layer. We talk so much about hidden layer. So like I said, hidden layer is actually like the most complex segment of the entire neural network. That's why your calculations are all to make sure you come to this output layer and you provide the right output. So after you pass y through the equation, ReLU and all, it outputs a value suitable to be used. So like I said, in the Titanic, a lot of people died. So output either whether they survived or didn't survive. So the output layer is usually calculated in terms of probabilities of the different outputs. So maybe like an example of like, let's say, not survived, there was 0.7, but for the people who survived is 0.3. So the final output will be like not survived and estimated to 1 because 0.7 is greater. So yeah, pretty much like that. So with that, we are done with explaining the basics of the neural network. Now we'll be having like a short 15-minute break.
So thank you, Karthik, for the wonderful explanation. So I'll now cover the next 15 minutes of the next around 30 minutes, 30 minutes of the lesson, which is a continuation. But first we have a quiz. Okay. So the test whether you all understand or not. This will be 5 minutes. So which activation function is designed to overcome the problems activation function X actually face? So A is sigmoid or B is ratified linear unit, which is ReLU. So could you all type in the MS Teams chat, which is the answer? So you have to pay attention or not? Okay. Don't want to think already. Very normal and it's fine. Okay, how about the others? Just try. It's either sigmoid or ratified linear unit. Okay, I give you all 5 seconds to respond. If nobody respond, I just review the answer. 5, 4, 3. Okay, Louis says it's both. Okay, unfortunately, it's not both. Okay, the answer is actually, I review the answer, it's actually ReLU. So, why is it not both? Is because, okay, sorry, I especially also correct that both are actually designed to overcome the problems that neural networks actually face. Okay, but in the question I could specify that function X actually refers to sigmoid. Okay, but Louis, you're also partially correct because ratified linear unit is used to overcome the problems sigmoid actually faces. Okay, for especially for sigmoid, right? There's this problem that face actually you can search up that it's actually called the vanishing gradient problem. So there were certain issues with the neural networks, right? When it's being trained over time, it was unable to really learn patterns very well, which ReLU actually helped to overcome the problem because it's able to turn it either on or off, which is like 0 or maximum number instead of 0 or 1 to round off. Because 0 or 1 is like more like squash. But ReLU is able to really overcome that problem. But to find out more, you could read up on like the initial research papers of neural networks itself when they first started neural networks and how they propose these problems. And actually, I think it's something out of the syllabus, but for ReLU, right, after they realized that ReLU actually helped in so many ways, okay, during the time where during 1990s that Karthik mentioned just now, right, it's actually like a period of winter period. So like when AI actually faced this thing called AI winter, right, it was unable to really do or perform the things that the industry actually really required. Which so that resulted in the neural networks not being very invested. So people stopped investing in neural networks. They stopped believing that AI actually could revolutionize the world. Okay, but then when this person suddenly came up with ReLU, this actually changed everything. This changed everything so that the prices, like how in terms of the investments of AI started to boom and everything started to flourish again. Okay, and then based on value, people find that it's so good that they started to develop other things such as leaky value, value with the G, and even LU without the R at all. So leaky value, value, LU. They actually went in other mathematical terms known as the Gaussian linear unit. Again, I'm not covering this in detail, but just know that these are some of the ways that counters the problems that value itself counted, so they were improving over time. And we're not sure how what will we go in the future, what kind of whatever new will come out in the future. But this is all there is to it for now. So second question, I'm going to tell you, ask another one. Neural networks, what does it mimic? So if you pay attention to our quizzes, you will be able to answer this one pretty easily. So A, B, or C in the chat. Okay. Jasmine, if you really very tired, you can rest for now. But okay, Jasmine says A. How about Louis? Are you sure, Jasmine? Okay, are you sure? Okay, that actually is correct lah. A is it mimics the biological human brain. I'm sure you all guys know that the explanation for human legs. Traditional programming in that sense that traditional programming used to be like, okay, when if this do this, hence if this happens, do this, if that happens, do that, right? However, in human brains, right, you don't specifically program it to do specific tasks, but it's rather that it adapts the things that traditional programming cannot deal with itself. So like it's a bit like you are firstly applying the neural networks to memorize things that cannot be explained by certain by just traditional programming, simple like if else statements. It won't be able to be explained that way. It's something that's more complex. Basically, the human brain could capture a lot of things, which is why it was so successful. So the answer is A. A. Okay. So now we're going to cover building the neural network. We're going to summarize what Karthik and I have said. So building it together. In building neural networks, we combine linear equations with activation functions. And input data is passed through multiple layers of neurons, right? And every layer applies a linear transformation followed by activation function. So linear transformation, y equals mx plus v. W is the weights of the neural network. And then B, the bias. After each neuron does its own calculations, it then follows through a path of activates through that path of neurons and applying it followed by activation function. Whether that neuron itself is turned on or turned off, that will be decided by the activation function, whether it's activated or not. So you know in chemistry, right, there's this thing called also activation curve, right? So it's like if it hits a certain point of activation energy, it will start to show certain symptoms of the chemistry the reaction of the both molecules. So similarly, that's how it could work. If it hit a certain point, okay, it will go. Else it will stay as like not turn on at all. And through training, right, these neural networks learn to adjust their parameters like M and B and weights to minimize errors and to make accurate predictions. So we're going to cover this last point. This last point is not covered yet. How to make accurate predictions while doing back propagation. Back propagation, as you can see, is like forward, backward, forward, backward. It's like you're doing again and again. It's like repeat step 2, go step 2, go step 3, repeat step 2, go step 3, repeat step 2. And then you're going in that cycle in order to, until the certain stage is done, then you can stop the model training, stop, and then okay, turn output. This model is actually a good model because we have done it so many times of here, look. Okay, so we first talk about loss function. This is a bit mathematical. It looks like, whoa, why is there a scary delta symbol, scary delta sign? Why is there sub x sub I, y sub I? But bear with me, this is only this can be explained in very simple terms. Okay, so it used to measure the difference between predicted output and the actual output. So common loss functions include, pay attention now, mean square error and the cross entropy loss. Okay, we'll ask something about this later. You understand that this is actually the y-intercept, and then this is our gradient. So our gradient is w. Then y equals mx plus b. This is actually our b, and this is our w, the gradient. W is delta y over delta x, and then all that. So the loss actually refers to all this. You see these gaps here? They're actually difference between y pred. Y pred refers to the predicted value of y refers to what the model actually thinks it is versus the actual y. Actual y value refers to the things that actually happen, but the model actually has some error. So I'm going to give an example of y pred minus y pred minus y, or even they even revert the other way, y minus y pred, because both are going to be the same anyway. First, we're going to do convert pass. Okay, the input is fed into the network, and activations are calculated layer by layer until the output is obtained. And then each layer's activations are computed using W and V. And backward pass, gradients of loss function with respect to the network's parameters, weights, and biases are then calculated. These gradients of loss, we'll discover this later, and it's done by the chain rule calculus. We don't cover chain rule in this case, but if you want to look more into it, it's actually AMAP. It's a bunch of AMAP. Okay, so backpropagation is the core algorithm used for training models to make predictions on the data. Okay, it involves propagating errors backward through the network to adjust the parameters to minimize a defined loss function. So step 1, error is calculated, difference between predicted and actual output. It backpropagate, pass back, error is sent back to each neuron in backward direction. And this gradient of error is calculated with respect to each weight. So it will go in tune itself, this weight, which certain weights that are supposed to be more activated, right? They will try and activate it, give more weight to it, and some of the weights that doesn't require that much will have less weight for it. So this is known as, it will be done as the gradient of error with respect to weight. So how is backpropagation calculated? So imagine this, you're at a party right now. Okay, so your lecturer wants all the students in the party to bring 5 pizzas to a party. So person A brings 4 pizzas instead, and person B brings 6. So person A actually be heard wrongly. I end up bringing 4 pizzas. Person B brings 6 pizzas. Then there will be some error because it is not exactly accurate. It should be bringing 5 pizzas, but they bring 4 and 6 respectively. So imagine 2 people went to a party. Hence, error is calculated using the predicted versus actual equals -1, which is this is your y value, y pred value, and this is your y actual value. So y pred minus y actual. In the previous slide, it was like y pred minus y actual, correct? Just y pred minus y actual, and then 6 minus 5 is 1. Y again, y pred minus y actual respectively. So the distance between what it's supposed to be and what you actually had, the output, the predicted output is actually 1 and -1 respectively. But dear classmates, -1 pizzas is a little awkward to the model, and hence we try to apply absolute error known as ABS. So what does ABS actually do? ABS could revert from a negative to a positive value. So it forces negative values or to a positive value. So absolute function of -1 is 1. So we apply absolute to make this negative disappear. And after ensuring all errors are positive, right, we then take its average, which is 1 plus 1 divided by 2 equals to 1. And this is known as mean absolute error. So mean absolute error is basically, on average, what are the mistakes, the average mistakes that people make in comparison with the actual output. So this is formula. Although we don't cover math in detail, but you can see that you're taking the divided by n. Divided by n, and then the summation of the output value minus the predicted output value, and you're doing the mean absolute. You're trying to make it positive, and that is same as a variable for SMAE. Next, we're going to do backpropagation calculation, a continuated one. So a certain proportion of error is taken, right, as long as the learning rate. So take a while to digest this diagram. This diagram here, it goes all the way down and it's without conversions. Assuming that now that you briefly know how backpropagation works, right? As you can see, these weights are readjusted to minimize the error. So you can see the starting point. Let's let fx to be the loss, right? Then we are actually decreasing its loss over time due to model training. So you could imagine like as a number of scoops of, okay, so I always like to use give students like the soup analogy. So Imagine this, okay, you have a bowl of soup, right? And then a spoon. So a soup and a spoon, and the bowl of soup is actually full. So the first scoop you take from the soup, right, is gonna be a lot of soup in that spoon. So the first scoop is the most number of most amount of soup. And the second scoop, you take slightly less soup. Third scoop, by the time you scoop to the nth scoop, like literally the n scoop, let n be a big number, you'll start to realize that the amount of soup in the bowl will decrease over time. So the first scoop is a lot, you drop a lot, drop a lot. Second scoop a lot. Then suddenly you realize that less and less soup in your bowl. And then if you scoop, the more you scoop, the less of the soup is being scooped. And this is known as derivative of gradient, rate of change. Uh, so rate of change is just, well, gradient of loss. So if you learn A math, right, or even E math, basic E math, this is actually the largest, steepest gradient. So the gradient is like steep going down. It's like you can't even walk. It's like, whoa, whoa, it's like very steep. And then suddenly it's like you're going like slightly less and less and less until a certain point, dy dx or whatever, or f prime x approaches zero. So f prime x approaches zero is known as the minimum loss. And when we know that it's at its minimum point, we call it the local minima. The local minima, right, it will just be stopped there and then be like, okay, this is the final value. So less loss means final value, and hence it will stop the model training. It'll be like, okay, the model has now learned to minimize its losses. So when the student brings like 4 pizzas, it now brings 5 pizzas instead. Everyone brings 5 pizzas. The error is zero. You will even reach here, like all the way down to zero. And then you just, okay, you know that the weights are being tuned accordingly. Okay. For backpropagation calculation, right? Uh, again, there's not required to understand the math. Okay, it's just that the chain rule that's discussed. Again, chain rule is not covered, so don't need to worry. Derivative is known as the gradient of error with respect to weights. Again, the gradient error with respect to weights. This like is the example of this lah. Just know that when you want to tune a certain the weights of the model, right? It's done using its derivative. So the first time the derivative is actually quite high, and then it just slowly decreases over time until it reaches an approximate zero. And then the learning rate is a proportion of it. So the learning rate, if you can think of it as how fast the human brain or how fast our neural networks learn. So the higher the learning rate is, the bigger proportion. It's simply the bigger proportion of mistakes being learned at one go. If the learning rate is low, it's just like the smaller proportion of mistakes that's being learned each time. So I learned oh, I made this mistake. I learn it slower versus I learn in a very big portion. I learn mistakes fast, right? So I take the mistakes proportion and then correct it accordingly. And realize the beauty of math is how math could describe human thought process in just one equation. Like it describes the way we think already and how we study for our TYS as an analogy, right? We are always tuning our weights, right? So our old weight will minus the uh again the proportion of the error, and it be assigned to this new weight, and repeatedly repeats this for n number of times, and we call this technical terminology known as epochs. So n times, we call it n epochs. I'll stop here for 30 seconds, just take a quick while and digest it. Oh yeah, for the benefit of those who are participating in the recording session, right? You could just pause the video. So like, yeah, assuming that you guys are pausing the video right now and then taking time to digest, I will now move on to the next slide. So another quiz time for 5 minutes. So the quiz time, apart from MAE, right? Without the help of Google, we don't use Google. So is squaring this error possible? Just don't cheat, is squaring the error possible apart from mean absolute error? So just answer me yes or no in the chat. Okay, I so far don't see any responses. I give you all like 5 seconds. If not, it's fine. Okay. I still see no responses. Okay, it's okay. I'll just move on. So like, if you're paying attention, right, actually mean squaring error also removes a negative sign using squaring. So in that case, MSE also helps. And not just MAE by itself. So that's all for the quiz. You will then go through the benefits of neural networks, which is adaptability, right, which they can learn and make independent decisions, and parallel processing, right. Large networks can process like multiple inputs simultaneously, and so parallel processing, multiple inputs simultaneously, we can describe it as the many functions I've written back to the slide of this one, right? Many inputs simultaneously, you can process like 3 inputs at one go to one hidden layer node. So this like in parallel processing by itself already. Okay. And lastly, fault tolerance, right? Even if a part of the network fails, right, the entire network can still function, because even if one node is gone, right, we're still able to do some calculations. So, and that's not as fault tolerance, which is, I would like to show the example of this one, right? When one fails, it's still able to like continue to execute stuff, because this one is like, this node is not working. You can still go through other nodes to do outputs. And what are the limitations of neural networks? Okay, data dependency is when they require a large amount of data to function effectively. Large amount of data to function effectively is simply just that lah. If you have a lot of data, then it's able to learn patterns of that large data better. If you have too small of a data, right, you will not be able to pick up so nitty-gritty details that properly that well. So it also means like a larger amount of data would provide more accurate information and better context for the model to push the model to really learn better patterns. And opaque nature is often termed as black boxes. Okay, black box refers to simply you just don't understand what's going on in the neural network. And even if you don't understand after this lesson, it's totally fine, because at the end of the day, neural networks are very black box. It's like you don't see what's going on when you actually do the coding. Okay, but this I hope this theory brings you the insight to zoom into that black box. But if you look from the outside view, it's really just you don't know what's going on. You don't know how ChatGPT actually exactly works, because it's a black box. Because it's just challenging to understand and how they derive that specific decision. Like you won't know, like example, you won't know whether when this node fails, well, how you so sure this node you can take off this node to produce the output. You cannot explain it. You cannot explain it using a lot of theory unless you write a research paper for me, right? So this one, even if this node fails, right, you are unable to explain why it derived to the output that it's supposed to do, because so many calculations, there are so many things that are going on. You can only describe it using like summarized terminology and how other people develop their theories and then doing it. And then lastly, we have overfitting. So they can sometimes memorize this train data if the train data is like it's being too overly trained rather than learning from it. So I like to give this analogy like when students are doing their 10-year series in their secondary school, right? 10-year series, right? Let's say you do too much of, let's say you do a certain portion of 10-year series. I do 9 questions of physics MCQ questions, and then I do one actual O-level test paper on that physics question. So the 9 questions I get correct, and the 9 questions I also get correct. So that's a perfect model. You're getting everything correct. You successfully learn the training patterns, which is the practice questions, and the actual exam questions well, which is the test data, which we will be covering in day 1.2, right? Then, however, what if it happens if he memorizes the practice questions too well? Let's say he just memorizes uh the 9 physics questions extremely well, but then when it comes to unseen data, like data that is not being seen, like the physics question for TYS, it's not able to actually think and do, because it hasn't seen that question before, because it memorized too well on its previous data that is being learned, it's learned too well on its patterns. And that is why overfitting can occur, because it does actually very well on training data, but it's unable to perform well on test data, the actual TYS questions. So this gives you a very good insight. Okay, that was quite some information. For PowerPoint slides, you could scan this QR code. Okay, for those who are watching the recording, you can just pause it and scan it. Okay, and thank you for listening, and see you later after lunch. So right now it's like we are actually quite ahead of time, ahead of schedule, like 11:35. We are actually 25 minutes, 20 minutes early for the session. So I will give you all guys a lunch break. You have like an hour plus of lunch break. We will come back at around 1.
1 p.m.
So
yeah.
at 1, sorry?
Yeah, just me at 1 p.m. Yeah.
You can just meet at 1 p.m. Then we'll go through some practicals, because practicals could actually let you understand better in Python as well. See you.